Okay, so for F, the Dirichlet region, I'm going to say that it has center X, and P, which is going to be contained in F, is a fixed point of an elliptic hyperbolic, an elliptic rotation. I'm going to call it gamma in delta. Okay, so now I'm going to suppose that I'm in the Poincare disk model and that P is 0. I'm going to choose this so that the lines leaving P are actually are Euclidean lines. Okay, so here I have my point X and I have rotations. So I'm going to call this one is gamma of X and this one is gamma minus 1 of X. Okay? So now I'm going to look at the bisector of the line, hyperbolic bisector of the line between gamma X and X. This passes through P, and likewise the hyperbolic bisector here is my point P, which is 0. And what I know is that this region here and this region here, not in F. Okay, and now if gamma is, I may assume, is a rotation of 2 pi over k, where k here is the order of gamma. Okay, then this angle here is likewise 2 pi over k. Okay, and this tells me that if k is of order is greater than or equal to 3, then P must be a vertex. Okay, since and in certainly always on delta of F, since I have points that are arbitrarily close to P that aren't contained in F. Okay, so remains the case where delta, where gamma squared is the identity. So what I have here is a situation like this. I have X, I have P, and here I have gamma of X on the other side of P, and in between the two I have the bisector. Okay, so if P is not a vertex of F, okay, then P is contained in a possibly infinite segment delta F. Okay? Now I'm going to, in the next bit, I'm going to use the following claim that V in F is a vertex of F if and only if V is contained in at least 3 Dirichlet regions. By which I mean Dirichlet regions of the tessellation. Gamma F. Okay, well, if I have the V in F is a vertex, then V is contained in at least 3 faces of this 3 Dirichlet regions. Why is that? Well, first of all, I know that I must be contained in at least one other Dirichlet region, and if I look at the total angle of F at V, that gives me something that's less than P. If I look at any other Dirichlet region that contains F, then I must have an angle of at most P at that point, because it can't be 2P, I'm not contained in the interior of any other Dirichlet region, and that means that to get the total sum of the angles, I need to be in at least 3 vertices. Now, the thing that needs a little bit more work is the following. Now, if that I have that V contained in 3 Dirichlet regions, then I have that if V is contained in at least 3 Dirichlet regions, then V is a vertex, i.e. I have to exclude the following consideration, the one where I have my point V here, which is contained in F, and then on the other side of this line I have 2 other Dirichlet regions, F1 and F2. Now, why is that impossible? That is impossible for the following reason. Let's suppose it was like this, so I have V, which is here. Here I would have X, which is contained in F. Here I have an image in F1, gamma 1 of X contained in the interior of F1. Here I have an image, gamma 2 of X contained in the interior of F2. And what I know is that, so now let's consider these lines between X and gamma 1 and X and gamma 2. And what I know, so let's call this segment here S1, here let's call this segment here S2, and what I know is that the boundary between F2 and F is the bisector, orthogonal bisector of this geodetic here, which I'm going to call G2, and this one G1. Here I have another geodesic, so I know that S1 is orthogonal to G2, and that G1 is orthogonal to G2. So this gives me something here like this. Okay. So here I have G1, G2, S2, S1. Here I have a right angle. Here I have a right angle. Here I have a positive angle. And what I get here, since I know that the sum of angles in a hyperbolic quadrilateral is less than 2p, that gives me that alpha is strictly less than pi. So these 2 segments, S1 and S2, cannot meet as cannot glue together as geodetics. Okay, so now in particular, for all gamma, any element gamma in gamma, since this is just permuting the Dirichlet regions, it sends vertices to vertices. So here, let's look at what gamma is doing. So here I have X, I have gamma X, and I have P, and gamma is inversing this this element. So there are two cases. So this is my, here I have F somewhere here, two cases. One is that the segment bounding, let's call this geodesic S bounding F on S has a vertex, contains a vertex, let's call it V of F. In that case, gamma V is another vertex of F. The segment V, gamma V, is an edge of F, and gamma is a symmetry. The gamma V goes to gamma V. V is a hyperbolic isometry fixing P. Fixing P. And the second case is the one where delta F intersected with S has no vertex and is therefore equal to S. And delta going from S to X is a symmetry fixing